I need to start.
Starting now. Don't miss the beginning. It's the most important part.
What's your first name?
Right now.
Like Irish?
Okay, welcome back to part 2 of lecture. Now, last week I gave this whole explanation about how you should interrupt at any time, and the lecture, I didn't get nearly as far as I should have. Today, I looked into extending to have a part 3. That's not going to work, so I've got to get through all the rest of the material today. So we're going to race through this. No comments or questions. Hold them till the end. And I took out extraneous stuff. I will skip through things that are not important. We got to get to the end. The lectures are free, but if you enjoy them and are able and want to make a donation, any size is welcome. The donations, none of the donations go to me. They all go to supporting Beyond Baroque. I encourage you to support this great institution in Venice. As I said, I don't take any money. So if you want me to speak anywhere at your club or church or party, whatever, I do that for free. So moving onwards, we talked about how weird light is from quantum physics. It turns out it's not just light and it's not just energy. This was postulated by Louis Victor Pierre Raymond de Broglie, the 7th Duke de Broglie. So he has royal background, but he was a student at the time, and he wrote his dissertation to get his doctorate degree, where he proposed that all this weirdness also applies to things with matter. The professors on his committee, they weren't sure what to make of it. They, in the old days, they would have said, that's ridiculous, tell them to go back and work on it. But after quantum physics, they thought, well, gee, things are so weird. Who knows? Maybe he's right with this crazy idea. And one of them came up with an idea. Let's mail his dissertation to Einstein and see what he thinks. So they waited, there was no email in those days. They waited for the email to go to Einstein and to come back, and Einstein said, give him his degree. The guy's brilliant. What he actually said was, he has lifted a corner of the great veil.
Wow.
Quite a commendation coming from Albert Einstein. Well, a few years later, de Broglie's work was all theoretical. A few years later, someone did the experiment, the double slit experiment, but this time not with photons, with electrons, things with actual mass to them. Everybody knows that an electron's a particle. It's a particle, and they found out that it worked. So once this was demonstrated, de Broglie got a Nobel Prize for predicting this, that electrons also are particles and waves. And Sir George Thomson, one of the people who did the experiment for this, proving that electrons are waves, he also got a Nobel Prize. Now, his father, the great Sir J.J. Thomson, was still alive. He was very proud to see his son get a Nobel Prize because 31 years before, the father, Sir J.J. Thomson, had gotten a Nobel Prize. And what did he get the prize for?
What?
He got the prize for proving that electrons are particles. He discovered the electron particle. J.J. Thomson, and 31 years later, his son gets a Nobel Prize for proving just the opposite. So it just shows you that this wave-particle duality is a family matter, right in the family, Quantum physics doesn't just apply to light, doesn't just apply to energy. It applies to everything. It applies to matter. So quantum physics matters. We've been talking a lot about photons and electrons. Let's compare them. One carries light, one carries electricity. Photons had been thought to be waves, and then they were shown to be particles. Electrons were thought to be particles, and they were shown to be waves. Photons always go the same speed. In a vacuum, electrons can go any speed under that. Photons are energy without mass. Electrons have mass. How much mass, you might ask? Everybody knows that. Equals mc squared, okay? And they both follow quantum laws. So you decide which team you want to root for here. Now, I started with electrons because they're the smallest particles that are easier to deal with, and that makes the effects bigger. But since then, more sensitive experiments have shown other particles, much bigger particles. It's more challenging to show that they also display wave interference, starting with neutrons. Neutrons vastly bigger than an electron, and much bigger than that even, is a molecule, and not just any molecule, but a really big molecule named after Buckminster Fuller, because they follow the same pattern as a geodesic dome or a soccer ball. And very recently, they've done even much bigger molecules were shown that they are also waves. So presumably everything is a wave, even us. So this says a lot about the universe. Everything is a particle and everything is a wave. And everything obeys these quantum laws. In principle, when you get to really big things, it becomes more and more challenging to demonstrate it. But they have seen 2,000 atoms acting this. Well, quantum uncertainty has some very interesting implications. And again, quantum uncertainty is an absolute proven fact, and it's very precise in exactly how much uncertainty it predicts. But it actually allows, the basic laws of physics can be broken, but only for a very short amount of time. It's limited. And it's kind of like the physics police. They're turning their back for briefly so that quantum particles can get away with things, while they're not looking. It really is kind of like that. Even the fundamental laws of the universe are uncertain. So you can make absolute laws in physics. They're still there, but they're not so absolute because there's some uncertainty. They don't apply all the time. There can be exceptions made because of this uncertainty. And again, I'll just show you the interactive exercises, but we don't have time to go through them. So these illegal things that quantum particles do. Richard Feynman created what's now called Feynman diagrams. They show these impossible things. As in this case, this diagram, this is showing two electrons coming at each other, and then, two electrons coming at each other, and then because they have the same charge, they repel each other. And in the middle, you see that wiggly line, that's a photon. But it's not a real photon, it's a virtual photon, because this photon comes into existence and then disappears in such a very short interval that is within the uncertainty, which means it's uncertain whether this photon ever existed or not. They call it a virtual photon. It's like that photon came and went before the physics police had time to notice whether it was there, and they couldn't stop it. And they couldn't stop it and say, hey, wait, photon's not allowed here. And where'd he go? Where'd he go? So there's one example. On the right, you have a much more complicated example of a Feynman diagram, and you'll see a very interesting thing. Some of the arrows are going down. Okay, time is going up. Time is going forward in the up direction, and you see a few of the arrows here going down. So these are virtual particles which are going backwards in time. And you say, well, things can't go backwards in time. They can if it happens so quickly that the physics police didn't have time to stop it. So it's like, did these things exist? Did it really go back in time or not? It's uncertain. It's just a virtual process. So these virtual particles go back in time, but for extremely, extremely short amount of time. So it's hard to say, did it really happen or didn't it? So you're saying, wait, we can't go backward in time. That would mean I could go back and I could get my future mother to fall for me instead of my future father. Well, don't worry, because this only happens on a very short quantum time scale that's within the uncertainty, and so could not possibly lead to this grandfather paradox or anything like that. Okay, now interestingly, when Feynman published his papers on this, the papers came in 3 parts. And this was during World War II. The war caused the publication of the second part out of 3 to be delayed. And so it was kind of ironic that part 3 ended up getting published before part 2. Whoa, going back in time there, part 3 and part 2. Well, another kind of impossible thing that can happen. Okay, I mean, you know, it turns out that Cinderella's fairy godmother was right. Impossible things are happening every day because of quantum uncertainty. One thing is called tunneling. And here's a picture of something called a tunnel diode. This is in all your phone and all your electronics and computers. What happens in a tunnel diode is called quantum tunneling. And from an energy diagram, it's like there's a quantum leap going like from energy level 1 to, let's say, energy level 1 at another place. So it's a leap, but a leap that's not changing energy, but it's a leap going through, maybe there's a barrier, energy level 2 in between. So it leaps across. So the particle or wave, whatever it is, cannot possibly go up to energy level 2. It doesn't have enough energy for that. But somehow it gets past it and gets to energy level 1 on the other side, because it does have enough energy for that. And this is impossible, except that it could happen during a very short time. And so quantum uncertainty allows that particle to somehow appear on the other side, and now it's there. And how did it get there? That was impossible, but it's already happened. So, you know, you can't stop it now. So it's kind of like, you know, if you're trying to get lug a heavy rock over a ridge, and you don't have enough energy. You're too tired. You can't get over the top. But somehow that boulder could appear on the other side by quantum tunneling, and it's not an actual tunnel. There's no actual tunnel going through. It's just it got across as if there were a tunnel. So this is one of the strange things that can happen. So what's the difference between an auto mechanic and a quantum mechanic? Well, let's say you want to get your car into the garage. Well, the auto mechanic just opens the garage door and the car goes in. But the quantum mechanic doesn't bother with that. He just waits until quantum tunneling occurs, and suddenly the car's inside. What? The door never opened. This is what happens at the quantum level. Strange things like this. Also, you only need a quantum mechanic if your car has really small problems, really, really small quantum problems. Okay, well, you might say, okay, that's kind of interesting, but big deal. Who needs quantum tunneling? Okay, so maybe it makes your phone and your computer work. But do we really need quantum tunneling? Do we really need it? How important is it? Well, let's consider, here we have a process showing, can a proton from one atom get into the nucleus of another atom? Okay, so the proton is out here to the right side, and it can't get in because there's the positive charge repulsion. So the proton or the nucleus of one atom cannot get past that. It doesn't have enough energy unless it tunnels. Okay, so it tunnels, and somehow, even though it didn't have enough energy, this quantum process occurred very rarely, but there's a finite probability that even though it can't happen, it happens anyway, and the nucleus of one atom got into the nucleus of the other atom. So this is the basis for nuclear fusion. So so we say, okay, well, this makes future nuclear fusion reactors possible. Is there any other reason why it's important? Well, nuclear fusion powers stars, including the sun. So it comes down to this. Do we really need quantum tunneling? Well, do we really need the sun? Couldn't we get along without the sun? The sun, stars would not exist without quantum tunneling making this possible. Okay, let's get to something else very, very, very strange that the quantum uncertainty, quantum physics predicts. Paul Dirac used quantum physics and he analyzed the vacuum. He came up with the Dirac theory of the vacuum. You might think, why would there be a theory of the vacuum? The vacuum is empty. There's nothing in it, right? Why would you need a theory for that? Well, he came up with a theory anyway, and the theory is weird beyond imagination. He postulated that the vacuum is not empty. The vacuum is full. The vacuum is so full that there's no room for anything else in it. And when it's that full, then there's nothing in it, because the things it's full of are imperceptible. They have these things that are in what's called the Dirac sea in the vacuum. They have negative energy, no idea what that means. They have negative mass, no idea what that means. But the vacuum's full of them, okay? Already, it sounds like this whole theory is full of it, right? But there's nothing, even when there's nothing in the vacuum, there's lots of something. So it's getting crazier and crazier. And now let's make some room in the vacuum, okay? The vacuum was packed full. Let's make some room. So let's put in some energy into the vacuum. How much? Well, E equals mc squared is how much energy you need. And when you do that, you pop one of these negative energy, negative mass particles, you pop them out of the vacuum. So a particle comes out. The particle now has real mass and real energy. So it's now a real particle. So it comes out of nothing, comes out of nowhere. And even stranger than that, of a particle coming out of nothing, is that it leaves a hole behind. And the hole is something, because, see, we had a lack of a negative mass is a positive mass. So I know this is sounding very crazy, but it's predicting that this hole in the vacuum that's left by doing this is going to have a positive mass and a positive energy, and it was named antimatter. If you've ever heard of antimatter, that's what it is. It's a hole in the vacuum. So you pull something out of the vacuum, it leaves a hole, and the hole is also matter. So you have the lack of a negative makes it a positive, and so I have an exercise about that. You can imagine. Well, this sounds really crazy. I mean, this is like crazier than science fiction. But Dirac published this theory, and amazingly enough, other physicists started looking for it, and it was observed that he was exactly right, that this is true, that a vacuum can do this. You can pull particles out of it, and once you pull a particle, then there's an antiparticle, there's antimatter. So antimatter was actually found based on this theory, and quantum physics has made science become stranger than science fiction, because who would even think up something this crazy? I could not believe that the respected professors in my physics class were telling me something so ridiculous, so totally absurd, and they were saying it with a straight face like it was true, and it was proven. But it is. So when I was a grad student at UCLA, they announced that Paul Dirac had come from France. He had come to give a lecture. So I had to go to this. The main motivation for going to this was I had to see him. He had a Nobel Prize by then. I had to hear this physicist describing this crazy theory of the Dirac sea and antimatter, and I did. I got to hear that. Einstein described Dirac. This balancing on the dizzying path between genius and madness is awful. So we've learned the universe is not only much weirder than we know, it's weirder than we can even imagine. And again, all this is really proven. Antimatter is real. And then you might wonder what happens, or you probably heard what happens, when the matter and the antimatter, when they get back together again. Well, remember, the antimatter is the hole in the vacuum with room for the matter to fit into. So when they get together, the matter falls back into the hole, okay, and fills the hole. And now the hole is filled, so the hole's gone, so the antimatter vanishes. And in the process of doing that, the energy that went into creating them had to come out again. So E equals mc squared comes back out of the vacuum that was put into it to create matter and antimatter, and you have a lot of energy coming out. which leads to us to wonder what would happen supposing the great physicist Enrico Fermi, why did he get a stomachache? Well, first he eats the pasta, and then he eats the antipasta. And when the pasta and the antipasta meet, there you go, stomachache. Well, antimatter, people have wondered, well, what can we use this for? And unfortunately, as you might guess, one of the first things they thought of, hey, let's blow stuff up, let's make bombs. Fortunately, that hasn't been done yet, but they're also thinking about ways to power rockets. Can we get rockets to go, take us to other planets or maybe even other stars? They're going to need an awful lot of fuel. Antimatter has got a lot of fuel packed into a small amount of space. Could be good for that. Stephen Hawking came up with, this could be a way that we could see a black hole. And here's a simulation of what a black hole would look like based on the antimatter that's being emitted from it. And also people have proposed ways to treat cancer with antimatter. So these are all things that have been proposed, but it turns out antimatter does matter. It's already being used. There's medical diagnostic, medical imaging, positron emission tomography. Positron is an anti-electron, it's antimatter. And it can see things very sensitive, extremely sensitive imaging that can see things that no other kinds of medical imaging could see before. Like here shows examples, just by looking at someone's brain, you can tell, are they alcoholic, do they smoke, are they fat, they use cocaine, just by these very, very sensitive measurements. So already it's finding practical uses. Well, you might wonder, gee, this antimatter sounds pretty cool. Can I get some? Can I get some of my own? Well, it turns out that you can get some antimatter. All you have to do is get yourself a banana, and about once a minute, typically, the potassium, the radioactive potassium in a banana will emit, on average, a photon, one anti-electron, one positron every minute or so. And do we need to mark bananas as unsafe? No. It is way below dangerous level. Well, okay, so I've been talking about all kinds of weird things that come up in quantum physics, but in our daily life, we never see that because that happens at a microscopic level, these things. In our, what we call the macroscopic level, sort of the level of things where we see, we don't see one electron. We don't see one photon. We see zillions of them, okay? And these effects, they wash out, they average out. We only see the statistical behavior of a jillion photons, okay? We don't see the one photon going through one slit or the other. We see jillions of photons and what they do on average. But you might imagine, what would it be like if somehow we could shrink down to be in the quantum world, like Ant-Man, and get down where these quantum effects became observable just in fiction? And there are a few books about this. You might wonder, after Alice went to Wonderland, where else would she go? Well, Quantum Land, of course. She's got to go there. And there she has discussions. She talks with photons and electrons about their problems and concerns. She tries to help them out. In the middle there is a really weird book I found. Imagine this lecture as a comic book, okay? There actually exists such a thing that you can get. I'm not sure if I recommend it. It's quite weird, but you might want to take a look at it just to see. And then on the right, Mr. Tompkins Went to Wonderland. This is a great book written by a real physicist. He's actually a student of Niels Bohr, one of the greatest physicists of all time. And Mr. Tompkins is this retired accountant who, he's not sure what to do. He likes to go to the local college and he sits in on the physics lectures. He doesn't really understand what's going on, but he hears it. And then at some point during the lecture, he nods off. And then he starts dreaming about the lectures. And he has these weird dreams where he's talking to electrons and photons, kind of like Alice. It's a great book. I strongly recommend that. And by the way, if you'd like a book list of these and other books, you can email me. I can send you that list. And another thing you can think about, and then as long as I'm giving books, here's a bunch of other books. The ones in green at the top are they're interest. If you have any interest in like Eastern philosophies, they tie in with that. I have no interest in that, and yet I loved the first book, The Dancing Woolly Masters. It's such a great book that even someone like me who has no interest in Eastern philosophy thought, wow, this is great stuff. So I really recommend that one. A few other books, including one by Werner Heisenberg himself, that, you know, and then a couple that on the bottom there, I had to include just, the titles are so great. I mean, Banana World, Quantum for Primates. I mean, you've got to love a book like that, right? How the Hippies Saved Physics. That gave me a lot of great stories. I'll talk a little later about the hippie physicists and all. And again, I can send you a list of all this. So what does the Schrodinger wave equation say often is that, you know, if it's not one thing, it's the other thing. It's taking two mutually exclusive events, like only one can happen or the other can happen. They can't both happen, and it's putting them together in the same equation. Okay, for example, the photon went through slit A or slit B. They can't both happen, but we take a superposition of both possibilities and we put them together in this Schrodinger wave equation. And how do you understand what that means? Well, Schrodinger, who invented this wave equation and its terminology, he takes the ensemble interpretation, interpret it in terms of a statistical ensemble. And all it means is that we're saying that in this case, like 50% of the photons go this way and 50% go that way. That's simple enough, right? But there was another interpretation started by Niels Bohr. And since he lived in Copenhagen, it was called the Copenhagen interpretation. And he said it means that both things are happening simultaneously. And I never understood this, but somehow this became like, he was so powerful, he had so many followers, that like the great majority of physicists accepted, this is the way we understand it, even though I don't understand it. But saying that even though two realities are mutually exclusive, the photon goes here, the photon goes there, it can't be both. Somehow they're both happening, and you'll hear many physicists say the photon goes through both slits, even though we prove that can't happen, and yet they say it does because, I don't know, I can't make sense out of it. Which leads us back to the old joke, why didn't the chicken cross the road? And the answer is, well, it was already on both sides, okay? Because its wave function was a chicken on the east side and a chicken on the west side. And you might think about other examples. But as I said, I've got to race. I've got too much material to cover today. You might wonder, all these brilliant physicists, Niels Bohr, one of the most brilliant people in all time, and all the people in his school of the Copenhagen interpretation, why would they accept something as crazy as this? Maybe it was related to where they got their funding. Their funding for Bohr's Scientific Institute in Copenhagen was funded by the Royal Danish Academy of Science, and their funding, it turns out, came mostly from Carlsberg beer. So maybe that was involved somehow. Well, as I mentioned a couple times before, and we'll see a recurring theme throughout the history of quantum physics, is Einstein, who basically started it all, was not happy with the direction that other physicists were taking his brainchild, and they were taking it in weird directions that he could not accept. He said, God does not play dice. No, things can't be uncertain. No, things can't be random. And he actually ended up spending much of the remainder of his life trying to disprove quantum physics, or at least the way that it had gone after he first proposed it. He thought, they're going in wrong directions. It's a mistake. They need to stop it. He's created a monster, and it needs to be stopped. It reminded me of another doctor, that created something, and then he realized, oh, we know it's out of hand. We need to stop it. So there's a lot we can learn, though, from these physicists. They had intense disagreements, like Einstein and Niels Bohr. Even though they had these huge disagreements, they were great friends, and they loved to get together. Einstein and Bohr, in particular, would always try to be together as much as possible, and they would get into these debates. How about this? How about that? What if you take this case? What if you do this thought experiment? They'd go back and think about it and say, aha, I've got it. Here's the answer to your thought experiment. So even though they had big disagreements, they got along well. Okay. In fact, Einstein was the one, even though he disagreed completely with Heisenberg, he said to Heisenberg, you ought to go work for Niels Bohr. And he said to Niels Bohr, you ought to get this guy Heisenberg, you ought to have him come work for your institute. And he was the one that got them together, Now, even though I personally, and a lot of physicists don't like Niels Bohr's Copenhagen interpretation, he was, for one thing, brilliant. He got Nobel Prize. He pretty much discovered how atoms work and all. He really was a really good guy. Okay, when the Nazis were invading Denmark, he escaped to Sweden. After he got to Sweden, he arranged to meet with the king of Sweden. He pleaded with him to offer asylum to all the Jews in Denmark. And as a result of Bohr's efforts, almost all of the 7,000 Jews in Denmark were saved from the Nazis. But there was one exception. There were some exceptions. One particularly notable one where the physicists had differences in philosophical views and could not get along was with Philip Leonard. Now, Philip Leonard, the original experiment, the photoelectric experiment that Einstein analyzed and published, and then got the Nobel Prize for that and started quantum physics based on that experiment was done by Philip Leonard. And Einstein had great admiration for Philip Leonard until, as they got into World War II, because Leonard had such great loyalty to the Nazis, he got appointed basically to be Hitler's top science advisor. His title was the Chief of Aryan Physics. He was promoting German science as the only true science, and any other science was deliberately misleading people. In particular, he picked out Einstein in particular and called him the Jewish fraud. Well, after that, Einstein didn't have as much admiration for Leonard after all. So there were limits to how well physicists could get along in spite of their philosophical differences. Well, two physicists that really did agree with each other on the philosophy, Einstein and Schrödinger, and they would talk and they would complain about the other guys, saying, how can it be both one thing and the other thing? They're mutually exclusive. And Einstein said, that's like saying, you have a barrel of gunpowder and then you have a barrel that's after it's exploded, and the one that hasn't exploded yet and the one that's exploded, they could be both exist at the same time. You could write down a wave function for both of those. So, Schrödinger completely agreed. Yeah, it's not saying that they both happen. It's just describing the probabilities, right? It's nothing so mysterious. We're just saying we can describe the probability this happens or the probability that happens, right? It's just common sense. It's those other crazy guys in Copenhagen that think it means both. Einstein's example was, it was not all that creative, but it got it inspired Schrodinger. You know, it got Schrodinger to start thinking, I really need a good example, you know, kind of like Einstein's gunpowder thing, but something that really makes the point. And I'm gonna try to explain why the Copenhagen interpretation is just nuts, you know. And to do that, he thought of an example, and it makes quantum uncertainty, dum dum dum, a matter of life and death. So he thought of this crazy example that you've probably heard of, where he puts a cat in a box. Now this is just a thought experiment. Okay, it's just something you think about to make a point, a Gedanken experiment. Gedanken is just the German word for thought. So you don't actually do this. Doing it would never prove anything except maybe that you hate cats. It's also something of a Rube Goldberg contraption. But how it works is you have a box, you put a live cat into it, and you put this green thing as some radioactive ore, and the radioactive decay is a quantum event, and you have a Geiger counter in there. It's going to detect when you get an emission, a quantum emission from the radioactive ore, and that's going to trigger the Geiger counter to trigger electromagnet, which is going to release, I'm pointing here, which is going to release the hammer. The hammer's going to swing down and hit this vial of poison chemicals. We're going to release poison gas. The cat is going to die if that happens. And what we're going to do is we're going to put it in, we're going to close the box. The box is completely sealed, so you have no idea what's going on. You can't see, you can't hear, you can't feel anything. You know, until the box is opened, you know nothing about what's going on in the box. And then we're going to turn on the Geiger counter for one half-life. In other words, we're going to turn it on long enough so there's now a 50% probability the cat is still alive and a 50% probability that the cat is still dead. Okay? And then, again, you might think about, anyway, something to think about. You might wonder, why did he pick a cat?
Yeah.
Why a cat? Why no duck?
Yeah.
You know, or something else. And let's go back to this photo I found talking about Schrodinger in his personal life. And you may notice his wife, Anne-Marie, is leaning down as if she's petting something. There's more to this photo. Indeed, she is petting something, and it's the Schrodinger family dog. There was no Schrodinger cat, there was a Schrodinger dog. Oh, that explains everything. Okay, anyway, Schrodinger thought this was important to make a point, and so he published a paper called The Present Situation in Quantum Physics. He published it in the most prestigious of all the science journals at the time, and in it he included one paragraph talking about the cat experiment, which of course he never did, but just trying to make this point. How ridiculous is it to think that the cat is both dead and alive? That's totally crazy, okay? So the Copenhagen interpretation, can we all agree that's just stupid now? So it got a lot of attention, and so whenever they would have meetings where physicists would get together, they'd end up arguing about it, because the supporters of the Copenhagen interpretation, they didn't give in, they were still arguing. Yes, the cat is both dead and alive, Schrodinger and Einstein were amazed. They're still arguing over this. They think the cat can be both dead and alive, and eventually the public heard about this and caught their attention, so much so that today you can easily find hundreds of different T-shirts with images of Schrodinger's cat on them. That's how popular this thing has become. My favorite that I've used on the left there is the idea that the wanted poster, instead of being wanted dead or alive, it's wanted dead and alive. By the way, Schrodinger's cat, what is its name?
Kitty.
Kitty? Its name is Hamlet. Why? Because the question is, to be or not to be. So, Schrodinger predicted that the wave function shows the probability of this can occur, that can occur, and that was firmly established by all experiments. All physicists recognized this was true, it was proven, but it didn't cover how did it get to the final result. You could write an equation for the probabilities of, for example, a live cat or a dead cat, but then at some point you end up with only one possibility. Okay, the cat is alive or the cat is dead, and it's got to, at some point it's got to end up with 100% of that. So the wave function essentially collapses to the actual result. And Schrödinger called this the collapse of the wave function, when you find out what actually happened, not just the probabilities of what will happen, but at some point it does happen. And now his theory, remember, was entirely proven to be correct, always makes the correct predictions of the experimental results at a probabilistic level, at a statistical level, okay? But the collapse to the actual levels, that lies beyond known science. And in fact, the Heisenberg uncertainty principle tells us we cannot predict when, where, or how the wave function will collapse. And that leads us to a story, okay? Dave wakes up in the morning. He's got a huge hangover. He looks in the mirror, he sees himself in the mirror, and he's so hungover, he doesn't know what he's looking at. And he's trying to remember, I was so blitzed last night. I can't even remember, which party did I go to? Did I go to Alice's party? And all the girls at Alice's party, they were crazy for me. They were all kissing me, and then, or maybe I went to Bill's party and everybody hated me there and they beat me up. I can't even remember, which party was it? What happened last night? And then his roommate said, you went to Bill's party. Well, now Dave looks into the mirror and suddenly it's clear, okay? No, he doesn't have lipstick all over him. He's got bruises from getting beat up. Oh, man, did you have to tell me that? Gosh, what a roommate, terrible roommate. I had to tell him that. What happened is Dave's wave function collapsed. He went from being in a probabilistic statistical state into finally resolving to the actual state of what actually happened. Either he was 100% at one party or 100% at the other. So what's our role in this? When does the wave function collapse? It seems to be like when we observe it. Is that what happens? It's like the classic philosophical question. If a tree falls in the forest and no one hears it, does it make a sound? It's kind of like if a cat dies and no one sees or hears it, is it really dead? If nobody can observe whether Schrödinger's cat is still alive, maybe is it still like in limbo between being both alive and dead at the same time? Einstein was talking to one famous physicist, to physicists anyway. We now know that when nobody's looking at the moon isn't there. Einstein couldn't believe his ears. He couldn't believe he was hearing this from a sensible scientific physicist. And he raised a very good question. Well, when you say that an observer looked at something and made it real, what qualifies? With what kind of look? Would a sideways glance from a mouse suffice to make the wave function collapse and reach, one result or the other? And yet we have views from brilliant physicists. Eugene Wigner also got a Nobel Prize, that there's a special role in quantum physics for a being with consciousness that's different from just a measuring instrument. It's suggesting our consciousness is creating the reality that it's conscious of. This is an idea that's been fomented by primarily by the Copenhagen interpretation, and has really gotten very much into our culture, that our being conscious of something is making it real. And if you ever wondered what kind of cartoons a Nobel Prize-winning physicist would make, these are some from Eugene Wigner. On the left, we see the old view of physics is that you have the observer here, you have the universe there, and there's this thick glass window, the very thick glass wall separating the two. I'm the observer, there's the reality, and the observer is just observing the reality. The scientist is getting an objective, impartial view of the universe without influencing it. And Einstein says, no, that view's out. In the middle, we see the scientist using his measuring instruments to break this glass wall, and now he is a participator. He cannot just observe the universe. By observing it, he is affecting it. And then on the right, we see another cartoon where the universe is bringing itself into existence by looking at itself, observing itself. So you get crazy things from brilliant people, brilliant scientists. And it makes you wonder, going back to the cat example, when is it decided? If the cat is both alive and dead, at some point it's either alive or dead. When is that decided? When does this quantum uncertainty, this ambiguity get resolved? And I'm sorry, I'm going to have to move questions to the end just because I have so much material to cover today. I have to get through. You can talk to me afterwards. So when does the cat become 100% alive or 100% dead? Is it when we look into the box, when we're conscious of it? What is actually making it occur? This collapse of the wave function? Is our consciousness creating reality? Knock, knock.
Who's there?
Quantum.
Quantum who?
Quantum uncertainty until you open the door. So, this teaching exercise created by Schrodinger about his cat, the cat in the box. What do we learn from that? Well, according to Schrodinger, he invented the wave equation, and of course he invented the idea of the cat in the box. According to that, all it is it's saying that the wave equation it predicts probabilities. It does not predict what happens in any one case. That leads to absurd conclusions. It's just not meant to do that. But according to Bohr, in the Copenhagen interpretation, it's showing the cat is both alive and dead at the same time. The photon went through both slits. The photon landed here and there, and somehow it's all resolved when we make the observation or when we look into the box. And all this about the Copenhagen interpretation, it makes you wonder, is something rotten in Denmark?
Oh no.
Meanwhile, the cat's mate is waiting for the box to be opened. What's going to happen? Is her mate still alive? May or may not contain live animal. If there's a radioactive ore in there, there's poisonous gas in there, and it's actually addressed to Schrodinger's address, his institute in Ireland. So you can think about what you learn from all this. So, let's talk about Jack Rosenberg. You may not have heard of him until after he changed his name. He changed his first name to Werner. Because he wanted to name himself after Werner Heisenberg. He loved Werner Heisenberg so much. And he changed his last name to Earhart, and he started Earhart's seminar training, you may remember from years ago. Like all kinds of weirdos, idolize physicists, all kinds of people, including weirdos. And about this time came arose a group of what were known as the hippie physicists, most notably Jack Sarfati, who was a very qualified, fully qualified, respected physicist. He was also a hippie and very open about it. Everybody knew him as, the hippie quantum physicist. Well, he got funding from Werner Earhart to show how quantum physics proves their principles of consciousness. He got a letter from a friend of his, Martin Gardner. He's a wonderful science writer, columnist for Scientific American. I've read all his books. He's great. He wrote, "Jack, my friend, you know too much science to be wasting your talents trying to get funding for theoretical work on consciousness. Do something honest instead, like maybe make a porno movie. His words, not mine. Well, he heeded that advice, not the part about the porno movie, but the part about quitting his work with EST, with Werner Erhard, and he broke off with them. And this breakup was really noted in the science world, and there were cartoons made about this wonderful event. The cartoonist, incidentally, went on to work on The Simpsons. Here are a couple of his cartoons where, on the left, the Jack Sarfati, the hippie physicist, is shown as Samson, and he's going to bring down the temple of Werner Erhard. You see his smiling face there, and his temple built on piles of money. And then on the right, again, we see Sarfati and Erhard, where, as Samson, David and Goliath. Well, an interesting consequence of the uncertainty principle is that when we observe something, we change it. And this has to happen because when we observe something, we're decreasing our uncertainty about it. We know, something, the certainty we can have about something is limited. And every time we get information, we're decreasing that uncertainty, so it has to appear somewhere else. The uncertainty can't just go away because it's fundamental to quantum physics. It's fundamental to nature itself. And so when we make an observation, something has to change. Okay, now whether it changes physically or just changes in the wave function is another question, but there is a greater uncertainty that comes about. And it turns out this has been demonstrated in many experiments. When you do an experiment where you learn more about a particle in one aspect, you now know less about it in another aspect. Okay, so when we make a change, the present and the future has to become less clear. So we make a measurement which makes it clear what was in the past, but the present becomes blurry as a result. I just illustrated this with some photos of Uranus. So how many quantum physicists does it take to change a light bulb? It doesn't take any, because once they've observed it, it's already changed. So you can think of other examples outside of quantum physics, things that change just because you know about it. Well, the uncertainty principle, as I said, it's actually very quantitative. It gives very exact results that you can calculate exactly how much uncertainty there is in this or that if you have the Schrodinger wave equation for it. Okay, for example, the most way it's often quoted is the way I've shown here. The delta means uncertainty. So the uncertainty in x, the position, and the uncertainty in p, the momentum, when you multiply them together, they have to be greater than a constant. That's the limit. So that if you're at that limit and you get you decrease your uncertainty about the position, you learn more about where it is, then you have more uncertainty in the momentum, and vice versa. And this could have some strange consequences. For example, a traffic cop pulls over a car. The driver happens to be Werner Heisenberg. How about that? And the cop says, "Sir, do you know how fast you were going?" And Heisenberg says, "No, officer, I don't know how fast I was going." The cop says, "It was 10 miles per hour over the speed limit." And Heisenberg says, "Oh, great, now I'm lost." If you got that joke, you really understand the uncertainty principle, okay? Okay? The cop told him how fast he was going. Now that he knows how fast he's going, he has much bigger uncertainty in where he is. So suddenly he's lost. Okay, once again, Einstein is complaining. Can this guy ever stop complaining? He's saying all this attention on what we know, it doesn't make any difference what we know. Nature was around long before we existed, okay? And it got along without us without any caring about how much we know about what it's doing. Nature must know what's happening, and that's all that matters. Doesn't nature know what's really happening? And so he claimed, well, quantum physics is incomplete. Okay, it doesn't account for what's really happening, regardless of what we know. So there must be some hidden variables that we can't know. So nature must be, what happens in nature must be determined by things that we don't know about, things that are hidden. And Heisenberg came back with, well, how about your theory of relativity? It doesn't have any hidden variables in it, and things are relative. Well, oh, wise guy, eh? And Einstein recognized he was caught. He said, yeah, it does, but it's nonsense all the same. Well, then along came Scottish physicist John Bell, who claimed, no, there can't be any hidden variables to explain what nature's doing that we can't observe. In fact, he had a great name for hidden variables. They're unspeakable. Not only don't they exist, we mustn't even talk about them. And he was able to prove it. The very famous Bell's theorem, he could prove mathematically that these hidden variables cannot exist. So what is really happening? This brings us down to basic philosophical questions now. What is really happening? You know, we're saying that if we can't know about something, it can't actually exist as a certainty. There's something inherently uncertain about reality itself. You know, and so we need to look at what is reality as compared with our perception of it. And so one thing we need to recognize is that we don't actually perceive reality directly. Okay, this is commonly known, this has been known forever, that our perception of something is different from what's actually there. Okay, we have limitations of our senses. For example, you know, we don't actually see 3 dimensions. Each of our eyes sees like a 2-dimensional projection of something. So like a cube looks kind of like a picture frame if you're looking at it from the center. Okay, we know it's not shaped like that, but we take our knowledge of it and we take the view from the other eye, we put them together, and we figure out, our brain figures out what it looks like in 3 dimensions, but we don't actually perceive it as it is. We don't actually perceive reality. Our senses are also inaccurate. They're not, you know, they're not exact. They're distorted by the environment. How we see something depends on the lighting, air turbulence, and also our biases. The way we think and our experiences and our present emotional state, what kind of mood we're in, whether we're drunk or whatever, affect what we see. And just as an example, without getting drunk, an example to show that our perception of reality is very different from what's actually there. Consider this is optical illusion here, one of my favorites, where we consider there are 2 squares marked A and B. And you look at that, and I'm sure everyone says, oh, the colors of those 2 squares are totally different. You know, A is one of the dark squares, B is one of the light squares. You know, those are absolutely different colors. Well, let's look at what colors are actually there. If we take away the context that our brain is using to put it into, and what we're going to do is we're going to take a mask to put over this picture. Okay, so the mask is going to cover everything except it's got 2 cutouts there, so we can only see those 2 squares and nothing else. So we can see what is the color of the actual light that's coming from those squares. And so all I'm going to do now is I'm going to reproduce that picture on the left, on the right here, and then I'm going to put the mask over it so you can see what shows through the mask. And what you find is that those 2 squares are the exact same color. Okay? So, you know, the way we perceive it is very different from what is there. Out of context, they're identical, and it's only our brain interpretation. No scientific instrument that measures the color of the light of those squares is going to see the colors as different. You know, any kind of scientific instrument you put on this square and the other square is going to see a difference between them. They're the same colors, and yet we see them very different. which leads us to a story about Pablo Picasso. Picasso got commissioned by a man to paint a portrait of his wife. So Picasso made the portrait. There it is. And the man looked at this portrait. He said, "What, are you nuts? My wife doesn't look like that. She doesn't look anything like that. That's not a portrait of my wife." And Picasso very calmly said, at the time that this happened, I believe this is a true story. At the time this happened, the wife was not present. And Picasso says to him, "What does your wife look like if she doesn't look like that?" And so the man reaches into his wallet and he pulls out a little wallet photo. And he says, see, there she is. She looks like that. She doesn't look like that. And Picasso takes this little wallet photo and he's studying it very carefully. And then he says, I don't remember her being so small. So his point is that an image of something is always different from the thing itself, from the reality itself. Okay? His wife does not look like a small photo. She doesn't even look like a life-size photo. She doesn't even look like a life-size sculpture. Whatever kind of image you make of his wife can't be the reality itself. It's always going to be different from the real thing. And so if the portrait is going to be different from the real thing no matter what you do, then it might as well look like that, right? That's as valid as a wallet photo. It's not reasonable to expect an image, which is our perception of reality, to look like reality. Okay, let's consider another artist. One of my favorites. Some of you know how much I like this guy. René Magritte painted this, and in French there, underneath the pipe, it says, "Ceci n'est pas une pipe," which means this is not a pipe. Some of you are looking at that and say, "What does he mean this is not a pipe? It's obvious that's a pipe," until you think, aha, I get it. That's not a pipe, it's a painting of a pipe. A painting of a pipe and a pipe are not the same thing. That's the point he's making. Incidentally, what is the actual title of this painting? If you know the answer, don't speak. But I'll give you a hint as to what is the actual title of this painting by telling you what it's not. This is not a title. This is not a pipe. And I'll give you another hint. The title is right in front of you. So anyone who doesn't know this, who hasn't seen this before, can anyone guess, based on those hints, what is the title of this Magritte painting? It's not "This is not a pipe," and the answer is right in front of you. Nobody got it? Okay. The answer is "The Treachery of Images." It says it right at the top of the slide. Oh. The treachery of images. The whole point of this painting, the treachery of images, is that our images, our perceptions of reality, are not reality. That's the point. Reality, perception, different things. We can never actually see something. We get a perception of it. What it actually is something different from that. And so this is a concept which comes up in quantum physics, and you can think of other artists, surely, who did that. Let's see. Let me go a little further. So it raises the question, well, if reality is not our perception of it, what is reality? What really is there? Okay, reality must be what's causing our perceptions. There's something real out there, and it creates in us these perceptions of it, which may be different, but they're caused by it, right? There's something really there, or is there really something there? Because now we introduce this idea, quantum physics can prove that there are no hidden variables. There are no things hidden in nature, which even though we don't know about them, they're still there and they determine what reality is. But that explanation has been proved mathematically. It doesn't work. So what is real beyond our perception, beyond what we can observe? Does it really exist? Is there really a reality? Quantum physics, it doesn't tell us about reality. It tells us what we perceive and what we cannot perceive. So we can make very, very useful predictions, predictions that have enabled the invention of every kind of electronics, digital cameras, lasers, all kinds of things I mentioned. They're very useful. The theories always work. And yet they don't tell us what's really there. And in fact, they suggest that there isn't something that's really there. All that we know about is what we determine, what the properties of it. We can turn on the computer and see what it does. We observe it. But what is actually going on with the electrons and the photons inside that computer? Unpredictable, and we can prove that will never be predictable. Quote from Werner Heisenberg: "Some physicists would like to think that there's a real objective world that exists whether or not we observe it, but with quantum physics, this is now impossible." So it's calling into question the existence of a reality at all. Is there really a reality, a definite objective reality that determines what we see? Well, how do we explain things at a quantum level? Well, physicists have a number of ideas of how to explain things, like the many worlds interpretation, which is also called the multiverse. But there are other ideas in physics which are also called multiverse. So we like to stick with the many worlds interpretation to distinguish it as the quantum physics interpretation, as opposed to various other uses of the term multiverse. And this answers the question that, how does God decide which quantum possibility happens? As Einstein was protesting, God can't throw the dice. God has to determine what happens. Nature has to determine what actually happens. So how does that occur? And the answer is, God doesn't decide. Nature doesn't decide what happens. There is no decision ever made as to what happens, because instead of that, the universe splits, so everything happens. So, for example, does the cat die or not? Well, according to this interpretation, the cat dies and the cat is alive, but those happen in two different universes. So you start with one universe, but then the universe splits into two, where the cat is alive in one and the cat is dead in the other. And so the decision of is the cat alive or dead was never made. The cat really is alive and dead, alive in one universe and dead in the other universe. And there's nothing random about it. You don't have to roll dice or guess as to which will happen. Will the cat be alive or dead? It's both happen. All possibilities happen. There's no randomness involved. And then there's no collapse of the wave function. There's no addressing this question anymore. The wave function never collapses. It's just the wave function what describes what happens in all of the many worlds, in all of the universes. And these worlds are entangled too. We'll talk more about entanglement later. An analogy could be like when an amoeba, this tiny single-celled atom in pond water, when it splits and it forms two daughter amoebas. So one amoeba becomes two amoebas, and these two amoebas, the two daughter amoebas, they have a common history. They were the same amoeba up to the split, but then after the split, they become independent, and they go off and do other things. So, one of the daughters could believe the cat's alive, and the other one could believe the cat's dead. They both happen. Or the formation of identical twins, same thing. Now, whenever the universe splits, I split too. We all split. Okay, so when the cat goes to this state of being either alive or dead, alive in one universe or dead in another universe, I, as the observer, I also have to split. So if I go in one universe, I see the cat is alive. If I go in the other universe, I see the cat is dead. And again, it's decided without the cat ever being just one or the other. The cat is both alive and dead. and without there being any randomness to the probability. So, for example, another question we could ask, maybe this morning you might have asked yourself, should I go to the physics lecture or should I stay home and watch sports on TV? And the answer is you do both. One of you splits into one universe where you go to the physics lecture and splits into another one of you that goes into the universe where you stay home and watch TV. Well, I personally find this idea ridiculous, as do a lot of people. For one thing, think about how many new worlds are being created, how often. It's not every time a cat dies in a box. It's every time a photon goes here instead of there, every time an electron goes here instead of there. Every single quantum decision, I mean, there are just zillions of these quantum decisions happening every second. And for every one of these, the universe is splitting. How many of these different many worlds are there in order for this theory to happen and to keep happening for every second for 14 billion years? How many of these many worlds are there? And this whole idea that anything that can happen, it does happen. So my own view is that, well, why would we even consider such a thing? This is just silly. But that's just my opinion, and I have to let you know that as much regard as you might have for me, other people that maybe have a better qualification than I have find value in this idea. Stephen Hawking, for example, is a proponent of the many worlds theory. So even though my tendency is to think it's silly, I have to think, well, maybe I'm missing something here. I'm not ready to say, oh, Stephen Hawking, he's a dum-dum, There must be something to it, okay? So what do quantum physicists do when life hands them lemons? Everything, okay? Anything they can do, they will do, but all of them in different universes. Can I communicate with the other me? This is something, one place, the Center for Intuition or something, they wanted me to come speak to their group, and they were asking about this. Can we communicate with our other selves in other universes? Well, the uncertainty principle tells us that can't happen. You can't communicate, can't travel, but they would still claim that they could sense somehow these other beings, not sure how, and some physicists claim someday it will be possible to prove the existence of these other worlds. I can't imagine how that's possible, but who knows? Another interactive exercise. And let's see. Maybe we should take an intermission at this point. And in the interest of getting through this on time, I'm going to say it's going to be exactly a 10-minute intermission. In 10 minutes from now, I'm going to restart the lecture whether you're here or not. Okay, so towards the end of it, we'll have people letting you know time to come back in, but we're not going to let this intermission go for more than 10 minutes. Okay, thank you.
Are you certain about that?
Yeah.
I have a question.
Yes.
Yes, if you remember me, we met.
Oh, Edmund?
Yes.
Yes, great to see you again.
In which world?
Yes, which world did we meet
I
in?
came here actually to hear more about the line of expertise that you are in with
The what?
this laser.
Oh, lasers. Oh, I have other lectures on that, but I don't give them here because they're kind of out of the.
I saw this lecture on lasers.
Yeah, I do that other places. Glad that so many people are so interested in physics. Okay, we're going to start. Okay, so this many worlds theory, what does it say about free will, the existence of free will? Well, every time we're faced with a choice, every time we're faced with an opportunity to express our free will, we choose all possibilities, okay, each possibility in a different world. Each one of the splits, according to this interpretation, each one of them is really us, okay? We are the one of us that ended up in this universe, but there are many others ending up in the other universe. They are also us. We all share a common history, okay? We all used to be us in the past, and now we're us in different presents. So when we have a choice to do something, we choose all of them, which is to say, we actually haven't made a choice, okay? If I tell you, everyone, raise either your right hand or your left hand, well, and you think, oh, I chose to this hand, or I chose to raise that hand. Actually, you didn't, according to this theory. According to this theory, you chose one in one universe, and you chose the other in the other universe. So you chose both of them. So you never exercised any free will. We already knew that you were going to choose one hand in one universe and one hand in the other universe. So you never made a choice. If you think that you made a choice to raise your right hand, that's only because you're the you that ended up in the universe where you chose the right hand. But the other you, which is just as much you as the other one, chose the left hand in the other universe, okay? So basically this is saying that there is no free will. We never make choices. We always do everything that can be done, and so there's never any choice. There's never any opportunity to express free will. Free will is completely an illusion. So maybe we have no free will because we never actually make any choices. Or in the words of Yogi Berra, when you come to a fork in the road, take it. Once again, with the griping, Einstein kept coming up with objections, as I mentioned, kept coming up with reasons to say, hold on, I didn't mean for you to do all this with quantum physics. And now he finally had him. He finally came up with an argument that was going to prove once and for all that all these crazy things they were getting out of quantum theory, his brainchild, cannot possibly be correct, okay? And what he looked at is something that Schrödinger came up with, is called quantum entanglement, okay? And that is when you have a wave function for two different particles, or it could be any number of particles, we'll say two, that share the same wave function. For example, you have one photon goes through this slit and the other photon goes through that slit, but there's one wave function that describes both photons. And because of that's saying that those two photons are entangled. They're somehow connected to each other. There's a connection between them where they don't exist independently of the other. So they came up with, at this point, he was a professor at Princeton. He had come to the U.S., and he worked with two of his colleagues there, put together a paper to demonstrate what he found as the paradox, which was going to prove that he was right about quantum physics being out of control. Their initials, EPR, became the name of this paradox, which is it's a thought experiment. It was a thought experiment at the time. It would be 40 years before it was possible to do this experiment. And even though it was just a thought experiment, it quickly became one of the most famous of all experiments ever, even though it took so long. So here's the experiment. We have two particles which are generated together, so they're entangled, okay? So one example would be two photons that are created by a single photon or an electron. In a way, they're very strongly entangled to each other. Okay, there's a very strong entanglement. Another example is when a photon creates matter and antimatter, an electron and a positron. That electron and the positron, they are entangled. Okay? And now what we're going to do is these two entangled particles are going to, we'll suppose that they're drifting apart from each other. When they're created in such a way, they're moving away, and they're moving further and further away from each other. And we're just going to clear a path for both of them. We're going to get everything out of their way, which might disturb them, might make any kind of observation or measurement, or destroy them or alter them in any way, and just let them keep going further and further away from them. And we're just going to wait patiently till these particles get arbitrarily far apart. So in principle, we could wait until these two entangled particles are at opposite ends of the universe. They could be billions of light years apart. Okay, now we're going to make a measurement on one of them. Okay, classically, we measure what's called the spin. So it's kind of like how something is spinning around like a top. And it turns out that if one of them is spinning one way, the other one must be spinning the other way. Just conservation of spin, so that when you create two things together, if one is spinning clockwise, the other one must be spinning counterclockwise. So when we measure one of them and we say, oh, this one's spinning clockwise, we know immediately the other one must be spinning counterclockwise, okay? Even though we haven't measured it yet. So we see at the bottom here, particle A has been detected and measured that it's spinning clockwise. So particle B on the other side, even though it hasn't gotten to the detector yet, we already know what the measurement is going to be. It's going to have to be counterclockwise. And if we measure it, it'll confirm that. Always does. So let me give you an example to illustrate, a simple example of how you can learn something indirectly and immediately just by observing something else that it interacted with. Okay, so my friend, he buys two identical pairs of shoes as presents, one pair for me and one pair for my brother. And so these packages of the two shoes, they're radioactive for some reason. He sends one package to me and the other package to my brother, far away. So these two pairs of shoes, at one point they interacted with each other, but now they're going to drift arbitrarily far apart, are going to go to me and my brother. I open my package, and I look at my package. Oh my gosh, he sent me two left shoes. What a numbskull. But one thing I also know, I know what my brother got. Even before, instantly I know what my brother got, no matter how far away he is, and without any communication with my brother, I immediately know that my brother got two right shoes, of course, right? Of course he had to get two right shoes. Okay, this is kind of like you learn the spin of one particle, it's clockwise, instantly you know that the other particle is counterclockwise without any kind of communication with it. Okay? So you can think of another example of something like that. There's a joke that quantum entanglement is easy to explain. Just consider two socks, right sock, two socks in a pair. You send them apart from each other, and then if I put one sock onto my right foot, then instantly the other one becomes a left sock, no matter how far away it is. And what's mostly funny about this is that I've seen it where people didn't know it was a joke. They thought, this is illustrating something about quantum physics. It's just a joke because there's no such thing as a right sock or a left sock. The sock goes on either foot, okay? And as much as I tried to explain it, they just didn't get it that it was a joke, and they kept saying, no, this illustrates this very important principle. Well, okay, so what I described so far about the shoes, there's nothing mystifying going on here, okay? It's very easy to understand. If this is the right shoe here, then the left shoe must be there. Okay, so there's nothing mystifying about this. what actually happens in the quantum entanglement is extremely mystifying. And I would like to explain that to you, but it's so difficult to explain. You'd have to know much more about math and physics to do it. It's a very difficult thing to make clear. And so I've seen many explanations in books and videos for lay humans. I've seen people try to explain this experiment, try to explain entanglement, try to explain why this is a paradox, and I was not happy with any of them. So I came up with my own, which kind of borrowed from the others and made it in a way that I thought was the best explanation of what is going on here. And as others have done, I'll use analogs, okay? So instead of talking about quantum particles, we'll talk about magical coins, okay? And instead of talking about which axis of spin, what axis is it rotating around, we'll talk about you get to choose which hand you're going to use to flip the coin, your right hand or your left hand. Okay, so that's going to be choosing which axis. And this is an act of free will. I could choose to measure spin along this axis or that axis. I could choose to flip the coin with my right hand or my left hand. So this is where free will comes into it. And when I flip the coin and see what happens, this experiment is an analog to measuring the particle spin. Okay, make a measurement, I get a result, heads or tails. And when I find what I get heads or tails, that's an analog to getting a spinning of clockwise or counterclockwise. Okay, so to make it simpler, I'm going to talk about these magical coins, but it all traces back to a quantum experiment. So I'm going to change things around quite a bit, but I'm going to try to do it in a way that captures the essence of the mystery of the EPR experiment and this paradoxical effect that comes from quantum entanglement. Remember our motto, good enough for lay humans. So, in this analog, you go to the carnival, to the Midway Games where people are throwing balls trying to knock down milk cans or things like that. And there's one booth called quantum entanglement with coins, and all they have there is 2 coins, a pair of nickels. The carny's sitting there waiting for someone to play this game, and he doesn't have balls to throw, cans to knock over. He just has 2 nickels. So you ask him, how does this work? He says, well, you put down your $1, and I take these 2 entangled coins here, and I give one to you, I give one to your friend here, and then you flip your coin, he flips his coin. Each of you gets to choose. Do you want to flip it with your right hand or your left hand? Each of you sees, is it heads or tails? And I'm going to make a prediction of what's going to happen before you flip the coins. And before you see what happens. And if my prediction is right, then you're out your $1. But if if my prediction is wrong, hold it, what do I do? Okay, if my prediction is right, then you lose your $1. But if I'm wrong, I'm going to give you $100. How does that sound? So you're thinking, well, okay, well, what's your prediction? And he explains, here's his prediction. Okay, I'm predicting that if you and your friend, if you both choose to use the same hand, so if you both choose, you're both going to flip with your right hand, both going to flip with your left hand, then I predict that you're going to get different flips. One of you is going to get heads, one of you is going to get tails. But if you choose different hands, you choose right, he chooses left, or vice versa, then you're going to both get the same flip. You're going to both get heads, or you're both going to get tails. Okay, so you think about this, and you think, okay, well, it's pretty obvious that we've got a 50-50 chance, okay? If you don't see that, just take my word for it. You got a 50-50 chance of being right or wrong. In the classical world, there's a 50-50 chance in the real world. So you're saying, well, what's going on here? I got a 50-50 chance. He's offering me 100 to 1 odds, okay? Something is screwy here. Something's fishy. Let me look at these coins. Okay, here's one of the coins. You take the coin, you try flipping it, looking at it, you know, it's not double-headed or double-tailed. You flip it, it doesn't do anything strange, you know. It flips heads about half the time, but not exactly. It doesn't follow any pattern. Perfectly normal coin. Nothing unusual about it. Okay? Normal. How about the other coin? Look at that one. Perfectly normal coin. Coin is perfectly normal. Okay? So what are the catch? Why are you giving me 100 to 1 odds? I can see that I got a 50-50 chance on this. There's got to be a catch. Why would you be offering me this? He says, of course there's a catch. And there's no secret to that. Why don't you just look at the sign right up here? Quantum entanglement. I'm not making I'm not hiding anything about why I'm doing this. I'm doing, the catch is that these coins are entangled. Okay? Each of the coins by itself, perfectly normal. But the two coins together, when you consider the two coins together, that is not normal because these are entangled. And quantum entanglement or quantum entanglement is not normal. Okay? So you're still not buying this, okay? This is still sounding awfully fishy. The guy must be cheating, right? He's got to be doing something to cheat. Like, you know, like, okay, well, you're going to see which hand I choose, and you're going to see how my coin lands, and then you go to my friend's coin, and he hasn't flipped it yet, so you're going to do something to make this coin land the right way so that you're going to win, right? You got to do something like that. And he says, okay, I'm just going to move you too far apart, so it's not going to be, so I won't be able to cheat, you know, so I won't have time to get over to your friend to, even after I see how you flipped and what hand you used and whether you got heads or tails, I'm not going to have time to go over to your friend, you know, way over there, to see how to do anything to control his coin. Okay, so I can't cheat. There's no possibility of me cheating. And so you say, well, okay, but you've got an accomplice, okay, and your accomplice is way over there with my friend, and you just send him a signal. You just got to get a message over to him. You send a signal to him, and you know, in this signal, it tells him, okay, one guy used his right hand, he flipped it, he got tails. Okay, you over at the other guy, you make sure that, you know, whatever hand he does, make sure that he gets heads or tails, the one that's going to make us win, okay? You just cheat by that. But the carney says, no, you don't understand. You don't understand. I'm going to make this absolutely impossible to cheat. When I said we're going to move you too far apart, I mean we're putting your friend into a Tesla Roadster and shooting it off to Mars. Okay, he's going to go off to Mars with his coin. And now, even if I had an accomplice out on Mars with him, there's no way that I can get a signal out to my accomplice, because it's going to take, you know, several minutes. It's going to take a few minutes for the information to get there, even if I could send him a signal. And by then he would have, you know, your friend would have plenty of time to flip his coin. Okay? So there's no possibility I could cheat on this. So you say, well, okay, so you just send your signal really fast. You send it faster than light, so it won't take a few minutes. It'll get there right away. And when you say that, his eyes open wide. What are you talking about? You're going to send a signal that's faster than light? That's crazy talk. Okay, so now comes the question of, why is that so crazy to send a signal that's faster than light? And for that, we have to get to the theory of relativity. So even though this lecture is not about relativity, that's a lecture in itself, for purposes of this experiment and to explain why you could not possibly cheat in this experiment to send this information faster than light, we need to consider theory of relativity. And this is a picture of the space-time continuum you may have heard Doc Brown talk about. In physics, this is known as Minkowski space. It was actually invented not by Einstein, but by one of Einstein's teachers. One of Einstein's teachers later on, after Einstein had come up with the theory of relativity, Minkowski then came up with the idea of space-time. and in order to illustrate the principles of relativity. So here's a picture of space-time in one dimension. Okay, we're going to have one dimension of space and one dimension of time because that's a lot simpler. So in this picture, up and down means up and down, okay? So we're not going to worry about east, west, north, south. We're just going to worry about up and down. So that's just up and down in this picture. And from going right to left is moving forward in time. So we're just showing pictures of how high things are versus time. And we're going to consider two things in this picture, a beam of light going up and a beam of light coming down. So you see one beam that starts at the bottom on the left and goes up, and that's this diagonal line that's going from lower right to lower left to upper right. That's a beam of light going up, and it goes at a certain slope because it's got a certain speed. And it comes up from below us. It comes up to us at the here and now, what I've labeled the here and now, and then it continues on going up as it goes into the future and goes up higher. Then we're going to take another beam that comes down from above, from the upper left. It's going to come down. It's going to go through us at the here and now, and then continue going down as it goes into the future. So we've got this picture of space-time with these two lines from light going up, light going down, and it divides it into four regions, okay, these four triangular regions, okay? So the triangular region on the left, that is the past, okay, that's where the past is. The region on the right, that's where the future is. So you might wonder, well, what about these other two regions? What are they? It's all relative. These are the regions where there's no past or future. It's all relative. It might be the past, it might be the future. It all depends on who's looking at it. There's no absolute past or future in those two regions, this kind of no man's land. Okay, so now consider that the light, okay, information traveling at the speed of light is going along one of these lines. And as long as it's going along one of those lines and goes to the here and now, it can't go into this relative region. And if it's going slower, then it's in the past or the future. But it can never be in this relative region. We can never get a message coming from these relative regions, the no man's land, the reddish regions. If we did, that might be a message coming from the future. So that would mean like a message that came before it was sent. How can we receive a message before the message is sent? Okay, you know, if you send a message into the past and it arrives before you sent it, well, that means, what if you changed your mind and decided not to send it? But it's too late to change your mind because it's already been received. So you get into all these crazy paradoxes about traveling into the past, you know, which they don't worry about too much in science fiction movies. But in the real world, these are really troublesome, okay, to try to affect things. You know, physics can't deal with changing things after they've already, changing what occurs after it's already happened. Sending messages that change things that have occurred. So anyway, this crazy space, you know, at the top and bottom here, it's just relative. We can't even talk about that space. We can't send messages. We can't receive messages there. And it's a lot of time-space. Look at how much of time-space is in this no man's land that is not in the present, it's not in the past, and it's not in the future. It's a lot. And if we try to make a picture of this in two dimensions, we see it's much more of the space. Now here's a picture where we're not handling up and down. Instead, we're handling both east, west, and north, south. And the arrow going up is time going into the future. You see that there's a cone. Everything within that cone, that happened in the past. Everything in the cone on the top, that's happened in the future. And everything else, which is like most of time-space, it's not in the past, it's not in the future. And when you go into, when you go into the real world, three-dimensionals, it's even more so that almost very little of time-space occurs in the past or the future. Almost all of it is in an area where past and future are undefinable. And as I mentioned, Hermann Minkowski was one of Einstein's teachers. And then you can try and think of some other examples. Well, we'd better follow this rule about faster than light because, the whole game of quantum entanglement, leading back to quantum entanglement, this paradox was started by Einstein. And so, of course, we're going to follow Einstein's rules of relativity. Einstein is not going to suggest finding a solution to this paradox by saying, oh, well, relativity is all wrong. Whoever thought that up was an idiot. We know that he's not going to say that. So remember, the ultimate speed limit of light, it's not just a good idea. It's the law. So sending a message faster than light, receiving it before it's sent, don't even think about that. And the bartender says, hey, buddy, no one's allowed in here going faster than light. An electron walks into a bar. Did you get that? The second half of the joke happened before the first half of the joke, because if the electrons are going faster than light, things can be out of order. Okay, so enough talking about this game of quantum entanglement. Let's go ahead and do it. Okay, let's play the game. So you play the game, you and your friend, flip their coins, you see what happens, and you lose. The guy won, you lost $1, but okay, you had a 50-50 chance, right? So you're not surprised. So let's keep playing. We're gonna, if we can win, we'll get $100, and then, then quit. So let's keep going. So we play it again and again and again, and we keep losing. You're thinking, well, I'm having a bad run of luck here. I'm losing every time. That's unlikely, but it's still, very possible. So let's keep going. Let's keep going because, and by the way, every time we have to get a fresh pair of coins because when you flip the coins, you've observed it, you've made a measurement, you've unentangled the coins. Okay, the wave function collapsed. So we got to start with new coins that are freshly tangled. And we're thinking, okay, I've got a running streak, but my losing streak can't last forever. One of these times I'm going to win and I'm going to get $100, and that's easily going to pay for all the other times when I lost. Okay, so I'm still going to come out ahead. So I'm going to just keep playing this game, no matter how long I keep losing. I'm going to keep playing this game because eventually I got to win. I'm going to get my $100. Well, you play 100 times and you lost $100. So, and as it turns out, no matter how long you play this game, you are never going to win. Because quantum physics says that it will always, the results will always follow the predictions of the quantum theory. So the measuring the spins of the particles will always give you the predicted result, and in this game, you always lose. So there was a catch. Why is he giving you 100-to-1 odds? Because he can't lose. He's following the laws of physics, and you're following your intuition, which is clearly all wrong. So you're thinking about this. Well, how can this be happening? Okay, I get it. Okay, these coins are entangled. They're magical coins. I get that part of it. Okay, there's something strange about these coins. Okay, I get that. But there's also free will in this. I got to choose. Am I going to flip with my right hand or my left hand? And my friend got to choose whether is he going to flip with his right hand or his left hand. And that comes into the determining whether you won or lost. How do the coins know which hand I'm going to choose and which hand my friend's going to choose? How do the coins know what to do in order to make me lose every time? It's not just that the coins do something magical. The coins do something which violates my free will. This is like much more disturbing than just coins that do something you can't explain. They're coins that know what I'm going to do. That's really scary. Okay, let's talk about action. Because this experiment, whether it's, particles or coins, it implies that something can affect something else even though it's very far away. Okay? And this is called action at a distance. Okay, this is a very old concept. As I had mentioned at the beginning of the lecture, long ago it was believed action at a distance was impossible unless you were a sorcerer, if you were the witch, trying to take the ruby slippers or something. You had to have magical powers to violate physics to have action at a distance. But it's long since been known by physicists that there's nothing magical about it. Anyone can do it. If you have magnets, you can have action at a distance. You can affect another magnet without touching it. Or with gravity, gravity can make the moon go around the Earth without touching it. You have action at a distance. Okay? But this idea was not always accepted. In fact, Newton himself was embarrassed by the fact that he used action at a distance in his theory of gravity. He introduced what he called so great an absurdity that he was embarrassed. Oh my God, I invented the theory of gravity. Oh, is my face red? Oh, I can't believe I did something so stupid. Introduce action at a distance. Incidentally, does anyone recognize who is the actor portraying the embarrassed? Yes, exactly. That is Weird Al Yankovic as an embarrassed Isaac Newton, of all people. Okay, well, physicists today, however, they don't have any problem with it anymore. The action at a distance, that's just part of it. But action at a distance has to follow two rules. One rule is that the action must get weaker as you get further away. Okay? Magnets, as you get them further away, they become weaker. Gravity, as something is further away, the force of gravity is weaker. When things are very far away, we don't, the magnetic attraction between them or the gravity between them becomes totally negligible, okay? Whereas in the EPR experiment, this entanglement experiment, we said it would work no matter how far apart you get. Okay, the other requirement, as we mentioned, is that the action cannot travel faster than light in a vacuum. Well, you might be saying, well, what about gravity? Gravity can travel instantaneously, right? I mean, supposing we have the Earth, orbiting around the sun, following this curved path around the sun, supposing that the sun, somehow the sun suddenly vanished. Well, now there's no gravity. Well, obviously, wrong way. Obviously, there would be no gravity. The Earth would stop orbiting around the sun that is no longer there, and the Earth would take off in a straight line, right? Right? That's obvious, isn't it? Well, as obvious that might be, it's wrong. It's completely wrong. What actually happens, that does not happen. What actually happens is that light is, not only is light coming from the sun, gravity is coming from the sun, and gravity is traveling. So the information that the sun has disappeared and gravity is no longer coming from it, that is traveling towards the Earth at the same speed as the light. It takes 8 minutes for light to get to Earth. It takes 8 minutes for gravity to get to Earth. And so the gravity is traveling for 8 minutes. It takes 8 minutes till it gets there. And after the gravity gets there, 8 minutes after the sun has disappeared, then gravity stops and the Earth goes in a straight line. So if the sun were to disappear for 8 minutes afterwards, the Earth would continue orbiting around the sun that's not there, because nothing can travel faster than light in a vacuum. Well, that's not the only kind of entanglement. Quantum entanglement is not the only kind of entanglement that stays just as strong over how great a distance. There is, of course, also romantic entanglement. We all know that no matter how far apart you get, it still is just as strong. And maybe you can think of other examples. Well, the action at a distance in the EPR experiment, in this quantum entanglement thought experiment, it happens immediately, okay? It happens, it's just as strong no matter how far apart the particles are from each other. We can let these particles get arbitrarily far apart from each other. The experiment still happens the same. And it must happen right away. So Einstein called this spooky action at a distance. That's a term you may have heard. And what he means by spooky is that this is not science anymore. This is just woo-woo magic wizardry nonsense, okay? This can't possibly be true. We're scientists here, okay? We don't believe in all that kind of garbage. And so, of course, this experiment could not possibly work the way that it's predicted to by quantum physics. So he concluded, okay, you guys, I finally got you. Quantum physics, the way that you've taken, it's wrong. Now I got you. We did an experiment. It can't possibly work the way you said. And so, it must be wrong. You can think of some other examples of way to do that. Well, if Einstein says something, he must be right. We know Einstein's never wrong, of course. Well, it took 40 years until they could develop the technology to actually do this experiment. Very tricky experiment to do. Unfortunately, Einstein was no longer alive by the time they finally figured out how to do this. And the experiment has been done many, many times at distances up to 800. Oh, I have to update that. Somebody did it more recently, and I think they went out to like 12,000 miles or something. The separation before they make this measurement. They've done this experiment many times. Oh, why is that thing there? Okay. And they found that Einstein was wrong. The experimental results agree exactly with the predictions of quantum physics. No matter how spooky it might appear, it still is true. And in fact, the Nobel Prize came up too early, but actually 3 of the pioneers in demonstrating this experiment got the Nobel Prize a couple of years ago. So one way this was described is that, Einstein said that if quantum physics were correct, then the world would be crazy. He was right. The world is crazy. So as spooky and as weird as these experimental results appear, they have been proven. So Einstein was wrong. The universe really is spooky. But you'll notice I put some question marks there, because some people, myself included, think this can't be the end of it. There's got to be something else going on. And if Einstein were still alive, he would figure it out. He would figure out how to explain this. There are some people who have come up with explanations for why the world is not spooky, why the world is not crazy. And I've read them, I didn't understand them. But the bottom line is nobody pays much attention to them because they're regarded as kooks. But if Einstein were alive and Einstein came up with an explanation, everyone would listen to him, and maybe we would find out some answer to this paradox, and some answer to why the world is not that spooky. So what have we learned about crazy ideas from this? What we've learned is that no matter how crazy an idea sounds in physics, it might still be true. Quantum physics has demonstrated that the craziest, most insane, most illogical, spooky ideas can still be proven to be true. So does that mean that every time that someone comes up with a crazy idea about physics, physicists should give it serious consideration? Is that what it means? No, it does not mean that. Why not? Because there are so many crazy ideas out there. I'll tell you, you don't have to look far to see thousands and thousands of these ideas come up with. And the difference is that people come up with ideas just because they feel like it. Something sounds cool, so here's an idea. The crazy ideas I presented, there was a good reason for presenting them, okay? Explaining experimental results that the old ideas failed at, okay? So we saw how the ultraviolet catastrophe, the photoelectric effect, the double slit experiment, quantum entanglement, there were results occurring from experiments that the current physics could not explain. And so there was a good reason to come up with some new explanations and eventually crazy explanations to explain these things. There was a need for these explanations. Whereas almost all of the other crazy explanations, they're what I would call gratuitous explanations. Nobody asked for them. There's no reason for them. There's no reason to come up with these. People just come up with them because, hey, wouldn't this be cool? Wouldn't that be cool? And they come up with thousands and thousands of explanations. And if physicists spent their time looking at these, they'd never get anything else done. Okay, so if you're going to come up with a crazy idea, start with a reason why this idea is needed, okay? Max Planck thought, hey, why don't we say there's quantum leaps? There was a reason he did that. Physics had failed to explain a specific event, okay? So new ideas should be taken seriously no matter how crazy they are, but only if they're not gratuitous ideas. If there's a reason for them, if there's a real problem that needs to be solved. Well, let's look at some other explanations, trying to understand what happened in this experiment. Let's start by this Carney who's running this experiment. Look at him closely. Does he look familiar? Oh, of course, he looks familiar. I recognize him. He's George Burns, right? No, not George Burns. He's God, of course. Right. The Carney is God. He's controlling nature. And if he's God, he has unlimited power. He doesn't have to follow the rules of relativity. God can do whatever he wants. He can say, okay, we're going to suspend the rules of the laws of relativity in this case. But isn't it strange? Why are the rules of relativity followed everywhere else except this experiment? You know, there's something very unsatisfying about this kind of explanation. How do you explain why the laws of physics work everywhere else, but they fail just in this case? You know, it's just not reasonable to think that. Okay, if you're going to say, well, God decides to break the laws of physics, how does God decide when? You know, it just doesn't make sense. So, if God doesn't arbitrarily choose to break the rules of physics in certain cases, maybe God knows what's going to happen. God can read my mind and my friend's mind and decide which hand and know which hand he's going to use to flip the coin, or what axis of spin he's going to measure. But now you're saying that there's no free will because, you know, if God or nature knows what you're going to do, then that means you don't have free will to choose, to make a choice. So this has implications. If you're going to think that it's determined what you're going to do, then you go into super determinism, where, or say that maybe God controls your mind. So you can't choose. You can't make a free choice. God decides what choice you're going to make. So again, you're reading. If you're going to, some of these ideas are going to lead you to conclusions that you might not like. You know, you might think about whether you really have free will. Maybe there's no such thing as random events. Maybe God doesn't throw dice, as Einstein said. And maybe what we think is random is actually the result of quantum entanglement. You know, so if quantum entanglement can occur at arbitrarily large distances, maybe, you know, things all over the universe are determining what's going to happen here. And because we can't keep track of all these things, it seems random to us. So maybe there's no such thing as actual randomness. And there's actually a reason that, you know, if you knew what's going on everywhere and could take into account all the possible entanglements, you could figure out what's going to happen. Another consideration here is, what's called a local theory. A local theory would say that, how things interact depends on how far apart they are. Okay, if things are close, they interact strongly. If they're very far apart, they interact more and more weakly. And if they get extremely far apart, you can consider them independently, that they have no significant impact on each other at all. But this experiment, the EPR experiment, seems to be saying that nothing is really local, because things can affect each other no matter how far apart they are. And so maybe there's no such thing as things being far apart. Really, they may appear to be far apart, but actually everything is close to everything else. Everything in the universe is all connected in a way that they're not really at different places. And distance between things is an illusion. And actually everything is, in a sense, kind of at the same place. This non-local view seems to be what is generally accepted among physicists. As crazy as it seems, I'm not sure why physicists can accept that. But, well, aside from the fact that all these experiments have basically proven that's how it is. It's been said the behavior of entangled particles is almost obscenely non-local. And then, of course, this could tie in with human consciousness, all these ideas about psychic phenomena, mental telepathy, claiming that human consciousnesses are connected. Maybe everything is connected in a similar way. Every part of the universe is connected to every other part in the same way that human minds might be connected. It's kind of consistent with the Copenhagen interpretation that our knowledge of things, our observations of things, causes wave functions to collapse and resolve the ambiguity. So here we're getting into an area that I would say is crazy, but, ridiculous, and yet there are experiments, physics experiments that won a Nobel Prize saying that something like this is happening. Another exercise thrown in here. Gee, it's only 4:15? Well, last week I only covered like a third of the lectures. And I figured that means next week I have to go twice as fast as I did this week. Well, I guess I've been doing a good job of going twice as fast because there's not that much material left and it's only 4:15. So I guess I didn't need to hurry as much as I thought I did.
Will you open to questions, Peter?
Yeah, I will certainly open up to questions. I'm amazed that I was able to get through the last 2/3 of the lecture in the same time that I got through the first 1/3. Okay, I didn't expect that.
Faster than the speed of light.
I guess so. I don't know what's happening. But, okay, another quote explanation of what is going on here that's been proposed is that particles, like the particles in this paradoxical experiment, they're going backward in time. Okay, like Merlin, the magician, lived backward in time, or Benjamin Buttons, they lived backward in time. And that means they know what happened because they're from the future. So they already know, what were the coin flips and all that and what spins were measured. They know that and they can act accordingly because they've already been to the future. So again, this sounds like a totally silly science fiction idea that I would never take seriously. But surprisingly, some physicists find value in this, and these physicists are somewhat respectable. For example, Richard Feynman, who also got a Nobel Prize, and he's one of the proponents of this idea that everything is going forwards and backwards in time. And remember, this is the guy who made these Feynman diagrams with the arrows going both up and down, things going forward and backward in time. So it's kind of consistent with that. And, if Feynman thinks it, I guess it's not as ridiculous an idea as it sounds like to me. Maybe time is a two-way street. And if Feynman's opinion isn't enough to convince you, let's consider what a real expert on the subject would say. And here's a quote from that expert. I think that the two components of the universe are actually one, wave and time. Time determines the shape and the length of the wave, wave equals wave. And the bottom line is you ain't going nowhere because you've already been there. And this is, of course, a quote from that great physicist, Frank Zappa, who also another quote from him, which shows a kind of insight on this problem. Without deviation from the norm, progress is not possible. And, you can see how relevant that is to the development of quantum physics. And by the way, this and the next slide are thanks to Jerry Fialko, who was here. A lot of this lecture was very influenced by Jerry. He and I had a lot of discussions about this during the development of this whole lecture. So it's only fitting that I put in a couple of slides devoted to him and to Jerry Fialko and to Frank Zappa. Some more ideas from Jerry about how Frank Zappa has worked his way into science. There is in the field of biology, there is a bacteria that causes acne, and so its scientific name has got Zappa in it because of one of the songs Zappa wrote. And another story is about how Zappa almost turned a theoretical nuclear physicist into a rock star. I won't go into that in more detail, but I will mention of just the opposite that happened, a rock star that became a theoretical physicist, and a very prominent one. If you remember Brian May, who was the lead guitarist who did all those, for Queen, who did all those amazing guitar solos in Bohemian Rhapsody. After the Queen broke up, he went back to school, got a PhD in physics, and he's very prominent now in astrophysics. I suppose some of his fame in that area is because he is a rock legend. Well, I also talked about Professor Feynman, Richard P. Feynman, and so I wanted to throw in the story of my own personal interaction with Professor Feynman. I didn't actually meet him once, but he was invited to be a speaker when I was at Harvey Mudd College. We would have a monthly colloquium, and we would invite a professor to come and give a lecture there. And one time they actually got accepted, for the guest speaker to be Feynman. He was at Caltech, so it was not far for him to come. He agreed to come and be the guest speaker at Harvey Mudd. But he said he didn't, instead of coming prepared with a specific subject that he was going to talk about, he was just going to field questions from the audience. So he would just come and the audience could just ask questions. Well, after that was announced, of course, all the physics students were thinking very hard to think, I want to think of a really good question to ask him, a question that's really going to impress him, So every physics student except for myself, I figured, let the other students think of questions. I'll just go and watch. So I came totally unprepared to ask any questions. And then they started taking questions, and the first question, which I'm sure the student had worked very hard to think up a really, really good pithy questions. This was right after the discovery of the psi particle, and asked, what direction do you think physics will take now with the recent discovery of the psi particle? And Feynman immediately says, north by northwest. Next question, okay? In other words, that's a stupid question. Give me a real question, okay? And then next question comes up. Again, a student who had thought very hard. Let me ask a really, really pithy, meaningful question that's going to impress this great man. What role do you see epistemology playing in the development of physics? Epistemology is a branch of philosophy. And Feynman immediately says, look, I'm a physicist, not a philosopher. Next question. Okay, so far things were not going so well. After these two questions, even though I'd come totally unprepared, I left out part of the story, an important part of the story. Okay. I forgot to mention that the host of the colloquium before he brought out Professor Feynman, he gave a little introduction, about Feynman's background. He said, I don't have time to tell you all the interesting stories about Feynman and his history, about the time when he did this or that, or about the time when, how he could never get away from physics, even when he went on vacation on a cruise ship. He spent his time like he was running around the cruise ship asking everybody if they had a yardstick so that he could measure the speed of the ship. Crazy things like that. So after these two questions and Feynman's disgust with these questions, immediately my hand shot up, and they called on me, and I said, Professor Feynman, how can you measure the speed of a ship using a yardstick? And he loved that question. I gave him the first question that he liked. You see, he got a big smile, and immediately he launched into an explanation of why I was looking for a yardstick. He was going to use this with triangulation to find the angle of the wake of the ship, and then he was going to use the viscosity of water and put it into the equation. He was going to figure out the speed of the ship from this. So one of my claims to fame is that I thought of a question that Feynman liked.
Yay!
So, how else can we explain this? Well, how can quantum physics be so illogical? Well, maybe what we think is logic is not what the universe thinks is logic. We're following human logic, the logic that fits our brains, but the universe, maybe it doesn't work that way. Our brains are different from the rest of nature, and maybe it doesn't make sense to us because we're not using the right kind of logic for that. It's hard for me to imagine, but how else can you explain this? Maybe nature is using strategy, kind of the way we do. Like what's called contrafactual reasoning is reasoning based on not how things are, but how they might be. And this is kind of reasoning that you might use like playing chess. So even though your opponent hasn't made his moves yet, you're thinking, well, if I move here, he's going to move his rook there, and then I'm going to do this, and then his knight is going to move here. And you're thinking about things that haven't actually happened. Maybe the universe works that way, and it's strategizing, trying, if we make this measurement, then it's going to do that, and who knows? How else can you explain it? Or maybe nature is just playing a trick on us. Maybe it's all a big joke, a big game that nature is perverse, and it doesn't want to do what we want it to do, to be logical. What could be more fun than tormenting logical physicists with illogical physics? Someone like me who believes so much in logic, and then I hear about the EPR paradox, and it says, but that can't happen, It's just, Einstein didn't believe it, but who knows? Maybe the universe is laughing at us. Oh, those crazy physicists, they think they can understand. Don't they know? So, but it doesn't even matter what physicists think about all this. We're doing physics, we're coming up with laws that work. Does it matter what physicists think about philosophy? Quote, details of a physicist's philosophy do not matter much. This came from someone you may have heard of, or you think you've heard of him. Actually, this is not the Charles Darwin you're thinking of. This is the grandson of the famous Charles Darwin, and he was a physicist. And he thought, well, who cares what physicists think about philosophy? So maybe you shouldn't listen to me on philosophical issues. So to conclude, what is the big question here? The really big question that is on all your minds, I know. The really big question is, what does this have to do with Oppenheimer, right? People keep asking me that. They've all seen the movie, and they think, oh, does your talk, is it all about Oppenheimer? Well, you'll notice that I have not mentioned Oppenheimer once throughout this whole talk because I didn't find an opportunity. But there are connections, okay? He was connected to everybody. Some of these showed up in the movie. Oppenheimer was a student of Max Born. He worked with Pauli. He was Einstein's neighbor. They lived near each other. David Bohm was a student of his who was admired by Einstein for his pilot wave theory. He supervised Feynman because he supervised the Manhattan Project, which Feynman worked at. He received the Fermi Award, and he extended the work of Dirac for the Dirac Sea. Oh, and we mustn't forget, of course, Born was also grandfather to Newton-John. But anyway, let's get to what is the really big question through all this. Why are scientists, all the opinions I've given you here about philosophy, they come from scientists, real scientists, not the quacks, not the scientist wannabes, real scientists, many of them with real PhDs and real Nobel Prizes, these respected, logical, rational scientists. Why are they coming up with these crazy ideas and following these crazy ideas? And the answer is that they're desperate. What quantum physics raises very strange questions. It shows very strange things. And so physicists are grasping at straws, trying to make sense out of things that don't seem to make any sense. And there's no good explanation that isn't crazy. Any sensible explanation has been proven to be wrong. So you got to throw those out. So physicists are desperate. They've proven that quantum physics is true. There's no doubt about that. But trying to explain it, there's no sensible explanation. So does everybody understand all this?
No.
Well, let's see what some physicists say. If you are not completely confused by quantum physics, you do not understand it. If you understand it, you would have been confused. Those who are not shocked when they first come across quantum physics cannot possibly have understood it. And a famous quote from Feynman, it is safe to say that nobody understands quantum physics, and he is, of course, including himself. So in conclusion, if you are completely confused by these lectures, by what I've been telling you, congratulations, you passed the class, okay? Thank you for your attention. Wow, I finished on time. So at this point, we can take questions, because even if they kick us out, we've gotten through the lecture. I want to remind you again, please make a donation. It doesn't go to me, but Beyond Baroque deserves your support. And I give other lectures, and you can arrange to find out about them or see them, or even to host them and to try to arrange them. I'm always looking for opportunities to perform, and I don't charge. So at this point, I guess until they kick us out of here, I can take questions finally. I guess I should have started taking questions before, but I was worried about getting through.
And see Poetic License in the Hollywood Fringe Festival this year.
Oh, excellent point. As I have noted here, I do a show, Poetic License. I play Poe. The Raven is played by... The part of the Raven is played by Leia Aquarian in the audience. She's also the producer, and we also have Paul Zolo in it. And actually I have a performance tomorrow with limited attendance, but we might be able to get you in. And I have other lectures on lasers. So at this point, we can open up to questions or discussions. Jerry.
Thanks a lot, Bradley. That was brilliant.
Thank you.
You can't prove you're sane unless you got discharge papers from a mental hospital. And reality is just a collect a punch. But you touched on Zappa. That was brilliant because, along with James Joyce, he knew that all times are happening now. That's called simultaneity. All that.
Yeah, right. It tied in with what Feynman was saying.
Yeah. In fact, Feynman and Frank hung out over the two drug singers. So. He said contrafactual.
Oh, yeah, here.
reasoning. This
Let's
is
go
what
back to that one.
Edgar Allan Poe invented. When he invented the detective novel, he invented reasoning backwards.
Oh,
It's
yeah.
called effects precede causes. So you touched on that. But how
Yeah.
is effects perceived causes related to wavicles? Because I don't know if you talked about wavicles.
Well, the wavicle is just a name for the wave-particle duality, the fact that things have been shown to be both particles and waves. So wavicle is just, putting the words together to recognize that, And last week I presented the pilot wave theory, which I subscribe to, which explains how things aren't particles or waves. They aren't a combination of of something that is like a combination of particle and wave. What they are is they're both things. There's a particle and a wave put together. Amy?
No, go ahead, but take him first.
Oh, Patrick?
Are we having another after party?
Oh, after party, of course. I do have to get to another party in the valley at 7:30,
Oh, okay.
but we have time.
My question
Amy, yes.
is, if, in addition to the question, who understands quantum entanglement and physics?
Yeah.
Who has experienced it?
Oh, who has experienced it?
That's another question as a tag on to that first question that you asked about understanding it.
Oh, yes, who understands it, who's experienced it? Well, yeah, well, we've all experienced quantum physics because everything that happens is a result of quantum physics, really. That explains how everything happens. Entanglement, have we experienced entanglement? Well, entanglement is also all around. You'd have to decide what it means to experience in quantum entanglement, and there would be a lot of disagreement about that. Many, different people would have different ideas about what that means, experience quantum entanglement.
Well, according to what you talked about, crazy.
Yeah, it's not clear. There are a lot of different
And
ideas.
It's probably not crazy for those people that have experienced it in dynamic.
Yeah, what's crazy to one person is not crazy to another, So, but even people who don't think it's crazy, I think anyone would have trouble explaining what's going on in quantum physics
Well, the
without.
difference is an explanation of what a cordon bleu sandwich tastes like, as opposed to actually experiencing the taste.
Oh,
inside the
yeah.
mouth of it.
Well,
So there's two different aspects of that.
yeah, a lot of things can be very difficult to
And
explain.
I'm interested in that question because I'm involved. I did some psychic research at UCLA in the early days in the 70s. And the man that I worked with, Dr. Barry Taff, he was in Dr. Thelma Moss's
Oh,
parapsychology.
I know a lot about Thelma Moss.
Beryllium photography and that. And so we would meet once a week, and this was pre-remote viewing. So,
Yeah.
Yeah, so I think there's the world of explanation and the world of experience. And the experience sometimes can give an explanation to the world of explanation.
Yeah. Well, a human experience is something that is way beyond what physics can explain. Okay, I mean that, they have separate fields for that, psychology and such, and it's far too complicated for physicists to
And
even
always an aspect. Psychology
consider.
is an aspect of consciousness, right? So,
Wait, what was the question?
no, it's not a question, it's
Oh.
a statement. It's just,
I heard a right at the end, so
you heard a what?
that a right was a question. You were asking me if something was
I
right.
was talking to myself.
Oh, to yourself. Okay. I thought you wanted me to answer whether it's right. And
Talking to my entanglement self.
yeah.
But you're talking about language. Before there was humans inventing spoken word, we all lived in an ESP world. Then. And no one was dead and no one was alive. No one was born. everyone just was, and we didn't have words that defined it. So as soon as we invented words, we fucked up everything.
Well, we knew when we invented words, we knew how to cast a spell.
That's it.
Yeah.
I'm sorry, we're gonna comment on that? I was gonna maybe take us, I have a question about, there's talk about developing a quantum computer. Is that an oxymoron? I mean,
Quantum, no, there are quantum computers. They've been built, they're very simple ones, at least.
or maybe that's it, because I guess, I think the guys are racing, those AI guys are racing to try to see who can get a functional, I guess, complex quantum computer. And apparently that's going to, I know without going into an explanation to me, but I mean, the plus and minuses versus the probabilities being much bigger than pluses and minuses, that is, I don't know how many gazillion times faster than the way that the binary computer works.
Yeah, there are ways you can describe quantum computers that will make it sound like, well, why would anybody want to use any other kind of computer, until you start to look into it and you realize that there are a lot of drawbacks of quantum computers, and it's not clear whether a quantum computer will be able, I mean, they exist, but whether one will be able to do something useful in the foreseeable future is questionable. In any case, I figured quantum computing is way too complicated a topic for this audience.
Because it seems to be in the media these days.
Yeah, there are a lot of things in the media which go way beyond
serious media.
I mean, I know there are a lot of articles on that and string theory and a lot of very advanced topics. I think to a lay audience, you can only give such a cursory explanation of them that they really haven't learned anything. So I steer away from those topics.
Sure, okay.
I try to think, cover things that anyone can understand on some level. So I don't want to talk about quantum computing or string theory.
Jerry,
Yeah, that's for you.
unsee Aquarians.
Yeah.
Oh, yeah.
Any other questions? Yeah, Patrick.
So when you're referring to how somebody's either decision or lack of being able to make a conscious choice because for free will being sort of an up in the air option, is there other worldly version, the doppelganger that we know from culture reference?
Doppelganger. You're talking about ourselves in other universes?
Yeah, so is that what the originally a doppelganger was pertaining to?
No, it was some kind of I think the term came from was it Dungeons and Dragons maybe?
Oh.
But they were talking about in this universe.
Oh. Okay.
You meet someone in this universe who is identical to you.
Oh.
So, whereas in the many worlds interpretation, we're talking about someone who actually was you. You and they used to be the same person, but the universe split. So now you're formerly the same person, and so it's like it's like when like an amoeba, one amoeba becomes two amoebas, or an identical twin. How an identical twin is formed. What used to be, if you can think of that as a person, it becomes two people who used to be the same person.
Or even a zygote will do that.
Yeah. Right.
Bradley, would you like to hear something kind of related on the group here?
Oh, well, give me a hint what it is. And
Well, Alea and I were in San Francisco, and we went to one of the oldest restaurants in San Francisco.
Uh-huh.
And this was just recently. And so I was so impressed with the pictures they had on the wall because I grew up in San Francisco and they were my childhood memories. So I started walking around and taking pictures, and then I came back to the table and sat down. And a woman came over to the table and she said, "I'm a best-selling author." And she said, "My name is blah, blah, blah." And she said, "I have to tell you something. I asked my fiance to stop staring at you." And she said, "Because I wrote you in a book that I have out in the public now." The woman had the same clips in her hair. She had the same color hair. She was the same size as you. And she said, "I'm blown away." And she was even dressed like you, that I'm seeing you here in San Francisco in this restaurant. She said she thought it was just amazing that happened. So kind of in the realm of spooky, that maybe she had seen me in another dimension at one time, and that triggered a thought. Or maybe she saw me walking on the street as a little girl and saw my consciousness in the future. You know what I mean? It's like so bad.
Yeah, there's a lot of strange things that happen, and most of the time they're not well enough documented that, or they're not reproducible. If something isn't reproducible, it's really hard to test it scientifically.
You can't reproduce the instant, right? Because it's the instant.
That's why science usually doesn't even try.
But
Science works with things that are reproducible. You can create something in a lab and you can create it consistently.
Right,
And
so that's
things that aren't reproducible is usually.
And how do psychologists get away with what they do?
Well, they look for trends. They look for trends, and
exactly.
something to the extent that things are reproducible, they can make predictions. There's always some degree of reproducibility, but when you talk about just
get you to the other side.
quirky, good luck with that.
I'll go with you. Thank you.
Yeah.
It really is a great opportunity for discussion. Had you ever listened or looked into the work of Russell Targ from Stanford?
No.
Yeah, he did a lot of documentation, and there was a man named Ingo Swann, and they would put him in concrete buildings down in, way down in the earth. And he could tell what picture somebody drew in another country.
Yeah. Well, I mean, if it were true, it should be very easy to prove it.
They did prove it. That's why I'm not telling you if you ever heard of them.
Well,
look up it.
Okay, a lot of things are claimed to be proven, and yet if someone actually has access to all the information about it, you can show that it's not proven. I mean, if it were proven, it would be reproducible.
Yeah, it was reproducible. But look into Russell Targ and look into Ingo Swann.
I know a lot about Thelma Moss, and do you know Louise J?
Yeah.
Who worked with Thelma?
Not like we used to go out and get massages together, but I know.
Yeah, okay.
Yeah. That to me is personal, like what she created was her belief system, her consciousnness around all of those things that she created. But I'm talking about Russell Targ is the physicist at Stanford. He's old now. He's maybe even deceased.
Yeah.
He was in his...
Well, I don't know anything about him.
But check it out. I mean, because I think it goes along with what you're talking about. Yeah, and I think it would expand it because I love how you just presented. It was phenomenal. Thank you.
Oh, thank you. Yeah, I'll try to find out more about him. Maybe send me an email to remind me his name, how it's spelled and all.
I'll send you a text message.
Yeah, because I'm not going to remember otherwise.
Yeah, I think you'll find it interesting.
Okay, thanks. Any other questions? So,
How
I guess...
handsome are you?
Oh.
As handsome as his dog.
How adorable are you?
Oh, thank you.
Amy. Amy.